Okay, welcome everyone again to the fourth day of talks in the Astronomical Observational Techniques and Instrumentation class. These are the final projects. Today's presentations promise to be some of the best that we've had so far. At least this day will be one of the top 4 days that we've had so far. And there'll be 2 talks. And the first talk will be given by Sabrina Levitan on the tilting galactic bar, and she's from the Rochester Institute of Technology.
Hello, I'm Sabrina. So I'm going to talk about the tilting galactic bar. So my question is, why is the Milky Way's bar tilted? So I'm going to cover how bars form, our galaxy's bar, the shape and symmetry of it. I'm going to talk about the velocity of the stars in the bar, the star clusters in the galactic center, magnetic field, and then hopefully give some answers. So the first thing I want to cover is, why do spiral galaxies have bars? And they're actually very common in spiral galaxies. They're a natural result from instability of the disks. So they happen when you start with your circular disks or circular orbits of the stars, and one area is more massive or more dense in one area, so that pulls the orbits and makes them increasingly elliptical. As you can see in the picture, where you start right here and then create your large bar. And you can see that over time it stays, so it's a very stable formation, but they can be destroyed if you inject enough mass into the system. And one interesting thing is that this is actually constrained by dark matter. So if the way to prevent bars forming is to lower the self-gravity of the disk, and that means move more of the mass of the galaxy into dark matter and have less of normal matter like stars and dust. So not really related, but interesting fact. So some facts about our galactic center bar. So the galactic center is around 8 kiloparsecs away, depending on your source. It can range from about 7.5 to 8.5. So several superclusters within it. I'm going to talk about the Archie cluster, central parsec, and the quintuplets. It's mostly late-type KM stars, including supergiants, which are about 3 to 7 million years old, and AGB stars, about 100 million years old. And there's a lack of late-type stars in the central 10 parsecs. The galactic bar is about 8 kiloparsecs wide, roughly, don't know exactly. Has about a total mass of 6.1 times 10 to the 9 solar masses, and it's made up of mostly red giants. So within the bar, you can see up here, here's like the entire bar from out here to here. There's actually an X-shaped structure in the middle. And that's a vertical X-shaped structure, so it extends out of the bar. It looks about peanut-shaped from our end due to its tilt. It's about 3 kiloparsecs wide and 1.8 kiloparsecs tall, which turns into about 0.44 arcseconds diagonally across, so it's not too big from our perspective. The arms of the X are about cone-shaped, so they're thinner in the middle and go out. And it's mostly symmetric around the galactic center and becomes asymmetrical the farther out you go. So, like I said, the density is asymmetrical with more of them on the outer edges. And from some of the graphs I looked at, it looked like one leg was denser than the other. So this one right here looked to have more stars in it. And based on several instability models, the X-shape is actually it's pretty easy to form if you start from a bar. And based on different models, you can get age around 5 or a few billion years. And most models show about 6 to 10 gigayears, so 10 billion years, about what I'm thinking, because most stars are red giants, and if you assume that they started around solar mass size or a little higher, that accurately follows their evolution. And actually a pretty common shape. Around half of spiral galaxies have a similar boxy peanut shape, how that's called. So I wanted to look into the velocity of the stars. So I wanted to see if I could confirm the elliptical orbits, because I'm assuming within the X shape, the stars start at one end of the X, go down and back up, then you have a cross. So I wanted to look at that. I wanted to find how far the stars have traveled based on their velocities. See maybe was there a common starting point, with they all started on one end and went to the other, and overall velocity trends. But to do this, I looked at BRAVA, the Bulge Radial Velocity Assay, which has been, or for over a few years, it got the radial velocity of several different stars. So here's a map of what they did, so that each of the data points is a collection of stars they looked at where they found the magnitudes, the velocity. They can't see it too well from where you're sitting, I think, but on the right it shows the sample data for one of those points. And what I was hoping to do with this data was look at a point down here and a point down here and compare the velocities to see if there was a difference in, like, see if one edge was moving inwards and the other was moving out, or to see if there was any interesting trends between the stars. Unfortunately, the data they gave you wasn't enough for that. They give you what they call VHC, which is heliocentric, and I couldn't find a definition of what they meant by that. You only have a positive or negative velocity, no direction. My guess is that it's like away or towards the sun, but I'm not positive, so I couldn't really use that for anything. What I did do was pick a point and look at the average positive velocity, which I assume was all in the same direction, and the average negative velocity. They're around the same, especially the lower end to higher end. So I took the average of that, which, assuming they're at constant velocity, which isn't the best assumption because the velocity will change depending on what part of the orbit you're in. But given that they'll be in a range of positions along their orbits, and that's been over 10 billion a year, I think it's a rough assumption to say that they've traveled about 830 kiloparsecs. And even if that's not very accurate, it still shows that they've orbited several times. It's not like they started here and now they're up here, they've gone around several times. What I could do though was look at overall velocity trends, because if for the collective data points, they give you our velocity compared to the galactic center. So this is velocity for different longitudes, and the x-axis is the same as the x-axis. You actually get a very interesting trend, I find, because there's a pretty strong correlation between positive and negative longitudes. So it seems to me like the data showing that the stars over here are moving more inwards and stars over here moving more outwards, assuming that the positive is moving towards the galactic center and negative moving away. So I'm not completely sure because I couldn't find definition, but that's my best guess for what the data is representing. So I think that I'm not completely sure what that shows, but my guess is that the two legs formed somewhat independently, so they're not like a bunch of stars all moving out. Some are going in, some are going out at the same time. Then next I wanted to look at was star clusters, see if they had any impact on the shape of the bar. So it says the Arches cluster, the quintuplet and central parsec. So the Arches cluster is made up of mostly Wolf-Rayet stars, which are about 2.5 million years old. And the quintuplets actually has two separate groups in it. So mostly there are Wolf-Rayet stars, which are about 4 million years old, but there's actually another group of stars that may or may not be related, but it's in the same area of KM giants and supergiants, around 30 million years old. And central parsec is more Wolf-Rayet stars, barely at 5 million years old. So compared to the age of the bar, which is estimated to be around 10 billion years, it looks like the clusters aren't actually related at all. They're the natural formation of stars, and they don't have any real impact on the shape. Although I did read one interesting thing about the central parsec, I think it was, talking about how dynamic friction could pull them in towards center, towards the galactic center. So dynamic friction might play some role in this, I'm not very sure. And lastly, I wanted to look at magnetic fields. So I looked at magnetic fields of NGC 1365, which is the Great Bar Spiral Galaxy. See a picture there, the very strong bar. And I'm assuming that most spiral bar galaxies are roughly the same. They'll have similar features, especially given that the X-shaped structure is so common. So I think it's a fair assumption to say that any overall trends in NGC 1365 we could compare to the Milky Way. And in NGC 1365, there's a strong magnetic field around the bar area, especially in the center, and it gets less intense as you move out into spiral arm, and it's very little when you're not in arm at all. It's actually very related to the gas density, so the more gas there is, the stronger the magnetic field. And it's strong enough to drive mass into the center of the galaxy at right around 7 solar masses per year, which I think I'd be very interested to look or to find more detailed information about the magnetic field in the Milky Way, because if there's a strong gas inflow in the Milky Way too, then that could move the mass in and sort of shape the bar, maybe that helped cause the bar to form in the first place, because it'd be more mass in one area, so more magnetic field in one area. So that's all the information I was able to find on the topic. So back to the question of why is the bar tilted. So the overview was that bars are formed from density differentials. If it's more dense in one area, then you'll end up with more elliptical orbits to form the bar. The X-shaped structure doesn't have much to do with the tilt because it can be modeled by instability, and it's pretty common. But the models don't specify that it has to be tilted. It's just a natural consequence. The general makeup of the bar is red giants, so about 10 billion years old. Dark clusters are much younger, so they probably don't have much of an effect. And there's likely strong magnetic fields in the bar area that could drive mass in the sensor. So there's not really a clear answer from that data why the bar is tilted. I'd like to go deeper into the instability model that people use, but I couldn't find more information about those. My best guess is that it's due to a mass differential in the bar formed. If it was more massive on one side, then maybe the orbit is stretched in that direction. And then it might be related to mass inflow from magnetic fields. In the future, I'd like to look more into magnetic fields in our galaxy. So there are some interesting information about two large gas dust lanes near the body center that maybe shifted themselves, so one might be lower down, one might be back, so they have a tilt too. I would really like to get more accurate velocities to trace the orbits of the stars, but velocities are very expensive to calculate, and there wasn't much data on that. And I'd like to compare it with other galaxies, because about half the spiral galaxies that have that same X-shaped structure, but I want to know if it's also tilted, that's very common, or if our galaxy is an enigma. And then some references.
Okay. Any questions?
Can you go back to the slide that had dark matter in it? No, okay, it's not what you do. So you said it's constrained by dark matter. I sort of zoned out. What did you mean by that?
So the bar dictated by like the self-gravity of the system. So the more mass in the galaxy, the more likely you are to form a bar, because there's probably a great chance of mass being concentrated in one area, which will cause the orbits. But if you move some of that mass into dark matter, so you keep the same overall mass of the galaxy, but more of a dark matter, it will lower the self-gravity of the system, so it's a less chance of the bar forming.
Okay.
When you say tilted, do you mean above the plane of the galaxy?
Yes. So it's a tilt of about 13
I see.
to 45 degrees. So like this here is closer to us than this part.
Gotcha.
More questions? See, I had a few.
Oh, I had another one. Sorry.
Yeah, go ahead.
So you said there's more, I guess, more stars. There's like a larger density on the left side of the X.
On the left or the
Yeah.
upward diagonal, this one.
Sure. Okay. Is that consistent? Was that consistent in like the other galaxy or all galaxies as well? Or?
I didn't have data for that.
Okay.
I'm not completely sure that that bar or that shape of like of the X is more dense. It just looks like that from the data, but it wasn't explicitly said.
Oh, okay. Sure. Can I see the other side?
Yeah.
Okay, I have a few questions. So here you you say that the bar is 8 kiloparsecs wide and 1.8 kiloparsecs tall. So could you point to those
So-
dimensions?
The bar itself is around here, which is 8 kiloparsecs, and then the actual structure within the bar is about 3 kiloparsecs wide and about 1.8 tall.
So there's an inner and outer region?
Yeah.
Okay. You just said 8 kiloparsecs for the outer region. That's not listed on this slide, right?
It was on the slide previous.
Yeah, so that was my question. So you don't have a picture of that, the outer?
Well, you can see how it's denser right here, which lines up to around 4, -4.
Uh-huh. Okay. What, that fourth bullet, what does that mean? Translates to about 0.44 arcseconds.
So this shape, like if you wanted to find stars that are just in this X shape, you'd have to look around 0.44 arcseconds around the galactic center.
Right, but that can't, something is not right about that.
I'm not completely confident in that number, but that's what I got when I calculated it.
It's, the X is 3 kiloparsecs wide, right?
Yeah.
So that's 3,000 parsecs, and a parsec is 25 arcseconds at the galactic center. So it's 25 times 3,000 arcseconds.
Then yes, the number would be wrong.
The decimal place. So that's a very big area, actually.
Okay. Yeah,
It's like half an arc minute per parsec, so that's 1,500 arc minutes, right? So that's 30 degrees, 40 degrees.
That would explain why I had trouble finding stars in that area.
Oh, because you punched in 0.44 arc seconds?
Yeah. Didn't get anything.
Yeah, there are a few stars that close. The S stars are at about 0.4 arc seconds. Go to slide 9. So these dots here, did you make this graph?
Yes.
So to make this graph, I guess you took the data in the table,
Yes.
and the data in the table included velocities, is that right?
Yes.
Did you go to that table?
This isn't the exact same table, but it's very similar.
Uh-huh. Does this happen to show velocities?
Yeah, this has velocity grids here.
And did you confirm these velocities? Did you make measurements, or you just took the numbers?
I did not have a way to make measurements myself.
But you could get the spectrum.
I couldn't get to work.
Oh, what happened when you tried to get the spectrum?
I don't know how to use FITS files.
Oh, okay. You could read them in IDL, read fits.
Okay.
It was on the homework, some of the homeworks you had to read fits. So you just read in the fits file, and then you can do a cross correlation with a vacuum rest version of a template spectrum from, there are places where you can download template spectra. These are all A-type stars, right?
Yeah.
These are like
Should be.
K-giants or something.
Mhm.
So you take these velocities, and then go to the next slide, is that the graph? And then you see this picture here.
So those are slightly different velocities. So the velocity on the last page were all the stars that were started at this area right here. So these velocities are I don't know exactly how they determine it, but there's different velocity for each point, while each point had several velocities inside of it.
So maybe each dot could be an average or
Yeah,
something?
that's my guess, but
Of the stars.
yeah, the numbers didn't quite match that, so I think there's something else different.
Maybe there's a selection filter that they used,
Yeah.
criteria. But this looks like rotation. Is that what you were saying?
No.
So is this not rotation, or it looks like stars are going towards the galactic center in a way?
I had positive and negative velocities, and so I'm assuming that they were towards and away from the galactic center, because I didn't have any other, there was no other information to say it was something else.
So this side is all positive, these are all negative, negative longitudes,
Yeah.
and that's this side.
Yes.
So is this what you would expect for a Templarian rotation.
What do you mean by Templarian rotation?
Well, just due to the mass that's contained within the enclosed orbit, the velocity that you can calculate. Maybe you didn't calculate that.
No.
So let's go back to questions. Oh, go to slide 11. Do you know how the magnetic field strength was measured?
It was measured by radio waves, I believe. I didn't fully understand the article, but it talked about different wavelengths and the polarization of those.
Oh, it's the Faraday rotation, is
I
that
think
it?
so.
Yeah, so it's the rotation measured. You measure the polarization as a function of wavelength, and that's a function of the strength of the magnetic field. Okay, any other questions? Okay, let's thank Sabrina.